Good morning. This is Aerodynamics Chapter 4. It is about conformal transformation. Under this topic, we are going to cover the introduction part of the conformal mapping. On the introduction, we can see a definition of conformal mapping and its application. Again, various type of transformation, which are elementary transformation of conformal mapping. Again, the application of conformal mapping for aerodynamics of aerofoil and for the Joukowski transformation. So we'll see these topics today. So when we start from the definition, a conformal transformation or conformal mapping is a mathematical mapping approach that preserves angle and shape of infinitesimal small figures while scaling and rotating them. So different operations can perform here. Some combination of, for example, scaling and rotation can have perform. Maybe enlarging and reducing size may happen without changing or preserving the angle. So it is a mathematical mapping that preserve angle and the local shapes through not necessarily lengths or areas. Such transformations are so such transformations are widely used in complex analysis. In the case of aerodynamics, in the case of electrostatic analysis, heat transfer and fluid mechanics. Therefore, these transformations are defined in terms of Jacobian matrix. So what is that Jacobian matrix? We can see later. And the Jacobian matrix must be positive and which must be positive scalar multiplied by the rotation matrix at every point. So we'll see the Jacobian matrix later. So this is actually the transformation, the conformal transformation or conformal mapping system. Initially, the object is in the XY plane, which is considered Z plane. Okay, so that Z is equals to X plus IY. So that is a complex plane of XY. So when we map or when we perform some transformation on this, we can find the transformed plane, which is W plane. So the W plane, which is represented with W is equal to U plus IV. So I indicates the complex plane. Okay, so the imaginary and real planes, X is the real plane and Y is imaginary plane, so we can represent the complex form in this manner. So a conformal mapping can be used to transform this complex plane Z into a new complex plane W, which is W is f of Z. So the W plane is what we call the transformed plane, and Z plane is the initial plane in the complex format. So the above figure shows that the example of example if W is equals to radical of Z. So in this case, W is equal to radical of Z. That means W is equal to radical of X plus IY. So that gives this kind of shapes. So every point in this Z plane, for example, pi is equal to C1, is represented here as pi is equal to C1 point. Again, pi is equals to 2, C2 is equal to pi is equal to C2, which is represented with green color. And the red color, pi is equals to C3, is represented with pi is equal to C3. And so we can see the shape difference, but every point indicated in the XY plane or Z plane will be in the UW UV plane, or which is W plane. Okay, so the variables X and Y in the Z plane have been transformed to the new variables U and V. and the transformed plane. So while this transformation has changed the relative shape of the streamlines and the equipotential curves, the set of curve remains perpendicular. Each set of curves, for example, curve in the xy plane are all straight here, but in the w plane curves are the curved shapes, and which are equipotential, and the set of curves remain perpendicular still. So this angle preserving feature is essential component of conformal mapping. So a conformal mapping can preserve angle and also scale distance locally by a factor that can vary from point to point. In terms of calculus, the transformation is conformal if it is Jacobian matrix at each point is positive scalar times a rotational matrix. And the infinitesimal small shape, such as circle, are transformed into other infinitesimal small shapes like ellipse. It can be changed into aerofoil shape and others through their size and orientation may change. So the transformation W is equal to f of z is called conformal at a point if it preserves the angle and the orientation between any two intersecting curves at that point. Therefore, we have z is equal to x plus iy is the complex variable in the z plane, which is the initial plane, and w is equal to u plus iv is a complex variable in the w plane, which is a transformed plane. So what is the condition for conformality? Transformation is conformal if and only if the f of z is analytic or holomorphic, and f prime of z, which is the derivative of f of z, should be different from zero at any point of interest. Okay, when it satisfies this, we call it as conformally transform. Okay, so that is the conditions. So this shapes provides us some kind of conformal transformation over different shapes. Okay, for example, if we see this shape, it is changed to this, and the function f changed this shape to this is the w. Okay, that is f of z. We have this shape in the A case, we can see this. It changed to some other shapes. Similarly, all the shapes indicate the conformally transformed shapes from original state to the second. So let W is equal to f of z, which is equal to u of xy plus I of ib of xy. So for the conformality, the real and imaginary part must satisfy the Cauchy-Riemann equation. So the Cauchy-Riemann equation shows that du dx, which is equal to dv dy, and du dy, which is equal to minus of dv dx. So this is called the Cauchy-Riemann equation. And for the conformal transformation, the real and imaginary part must satisfy these conditions. And this ensures the angle should be angle preservation and orthogonality of the coordinate curves. So this orthogonality means the coordinate curves are perpendicular to each other at every point. There are a number of transformation, that conformal transformation, among them some elementary transformations like translation, just without changing any shape or distortion, just shifting the object from one point to another by some distance. So W is equal to Z plus alpha. So alpha is a complex number which transforms the given plane, or W is equal to Z, to some distance, alpha distance from its original point. By this transformation, every point in Z plane is displaced in direction of alpha. Okay. The second is rotation. So rotation is one of an elementary transformation. So on that, W is equal to Z times e raised to I alpha. So this exponential e raised to I alpha, as alpha is real number. So by this figure, so this will make some rotation, performs rotation. So in Z plane rotates through an angle alpha in W plane. Okay. The third one is magnification or scaling, we can say. It can be scaling up or down. That means magnifying up or diminishing. So W is equals to alpha Z. So we are scaling the given plane by alpha amount. So the in W plane is magnitude alpha times than the size of Z plane. So size difference. Inverse also is the another elementary transformation, which is 1 over Z. And we have also combination of this kind of transformations also. So the above transformations is important for understanding some property of conformal mapping. Okay, so another bilinear transformation, which is the transformation is called bilinear. It is a combination of translation, rotation, and magnification and inverse together. Okay, for example, we can see AZ. This is just magnification. BZ over CZ is kind of another transformation. Plus D is translational transformation, so that for which A, B, C, D are different from zero are called bilinear transformation. So bilinear transformation, it is also called Toussaint transformation, and is a mathematical mapping used mainly control system and signal processing to convert the continuous time system from S domain to an equivalent discrete time system or Z domain. So what is the application of conformal transformation? Conformal transformation or mapping is an important technique used in complex analysis and has many engineering applications. Okay, one of that is the complex plane analysis. So on that, conformal mapping are often defined by the Cauchy-Riemann equations that map points and curves from one plane to another while preserving the angle. We already seen the Cauchy-Riemann equation, which is du over dx equal to dv over dy, and du over dy, which is equal to minus of dv over dx, is the Cauchy-Riemann equation, which we have discussed. Another application in the fluid dynamics and aerodynamics application. So it is used to transform complex plane patterns, such as those around an aerofoil, into similar shapes that are easier to analyze. Okay, so that is the technique. It is also useful in numerical analysis and algorithm development strategies in computer science, and we use it for image processing also. So conformal transformation are useful for tasks like image rectification, for correcting distortions in the aerial photograph. So that are the application. So let's see the common conformal transformations which we usually use. One is translation, as we have discussed earlier, or as we have mentioned them earlier. And the translation, W is equal to Z plus A. So the W plane is we have Z plane, that is X and Y plane. When we plus it shifts the given object. For example, if you see the real object or initial object with green card here, no color here, it is transformed to some image with the magenta color here. So this is so the amount it translated is A. Okay, it is in A translation. So it shifted the shape without any distortion. It shape. So we can see the shape the same. Here the image shape also the same. So a transformation is function that maps every point from one plane to another, usually from Z plane to W plane. W plane is the transformed plane, and the transformation is written as W is equal to f of Z, as we have seen. So here, Z is equal to x plus iy, and W is u plus iv. So Z is equal to x plus iy is point in the orthogonal plane, and W is equal to u plus iv corresponds to point in the transformed plane. So that is the meaning. The next type of conformal scaling or scaling. So scaling is another conformal transformation in which a figure is uniformly enlarged or reduced while preserving its shape and angle. So there is no shape and angle distortion, but for example, here a small object with corner ABC, triangle with ABC, which is scaled to larger size by A amount. Okay, so when W is scaled by A, Z is scaled by A, then it gives us such kind of large dimension without changing orientation and shape. So when A is greater than 1, we have magnification. When the scaling factor A is 0, then we have reduction, actually less than 1. If it is less than 1, reduction. If A is equals to 1, the shape will not change. It is remains same. And A is less than 0, scaling with 180 rotation. So that is the meaning. So during this scaling, we have W is equal to AX, A times X plus IY, which is AX plus IAY. So the real and imaginary part of the this transformation are U is equal to AX and V is equal to AY. So this is real and imaginary components. Again, rotation is another type of transformation. Rotation is conformal transformation in which every point of figure is turned through a fixed angle about the origin while preserving the shape and angle. Still shape and angle are preserved. So rotation through an angle theta is given with W is equal to e raised to I theta times Z. So this e raised to I theta is just cos theta plus I sine theta from the Euler exponential relation. Therefore, we combine them that W is equal to x plus Iy the whole times cos theta plus I sine theta. So from that, we can determine the real and imaginary part. So separating the real and imaginary, we can get u is equals to x cos theta minus y sine theta, and v, the imaginary one, is x sine theta plus y cos theta. So rotation is a conformal transformation given by W is equal to e raised to I theta times Z, which rotates every point in the complex plane through an angle theta without changing size and shape. That is conformal transformation. Now let's combine rotation and scaling together. So here we combine transformation like rotation and scaling transformation. So let W is equals to AZ and A is equals to REI theta. So here Z is equal to X plus IY and W is equal to U plus IV. So when we combine all of them, what we can get, W is equal to R times EI theta times X plus IY. So this gives us R scaling factor and the theta angle of rotation. So after a certain arrangement, we can separate the real and imaginary parts. From that, we can get U is equal to R cos X cos theta minus Y sine theta time, and the imaginary part is V is equal to R times X sine theta plus Y cos theta. So that is rotating and scaling. So these are A is equals to R, pure scaling. A is equal to EI theta, pure rotation. A is equals to 2 times E I 30, or which is theta. It is scale by 2 and rotate by 30 degree, meaning. And A is equal to minus 1 means rotation by 180 degree. So that is rotation scaling transformation. So the transformation W is equal to AZ, where A is equal to RE theta represents a conformal mapping that rotates figure by angle theta and scale it uniformly by a factor R, preserving angle and shape. So let's take some example. The Z is equal to 1 plus I is the given Z plane, and A is equals to 2 times e raised to I 90, so which is equals to 2I actually, because e raised to I 90 is nearly 1. Therefore, W is equal to AZ, which is equal to 2 times I times Z is 1 plus I. So this is, so 2I plus 2I square. So I square is minus 1. Therefore, we have minus 2 plus 2I. Now, the real part is 2, that U is equals to 2, and V is equals to, U is equal to minus 2, and V is equals to 2 here. So magnitude doubled. That means we have 1 plus I here, but here magnitude is doubled and rotated by 90 degree again. So this is the meaning. Inversion is another type. So inversion is a conformal transformation that maps points in the complex plane to their reciprocal. So inversion is reciprocal, that producing a dramatic geometric change while still preserving angle. Okay. So the inversion transformation is defined mathematically. W is equal to 1 over Z for Z different from 0. And the coordinate form for this is W is equals to 1 over X plus I, right? So when we multiply it by X, both numerator and the denominator by X minus IY, we can get X minus IY over X square plus Y square. So this is the, and from that, the real part is X over X square plus Y square, and V is minus of Y over X square plus Y is the imaginary part. Another last, yeah, just let's see some inverse. Let given Z, actually this is example, Z is equals to REI theta, then W is equal to 1 over Z is the inverse or inversion or reciprocal, which gives 1 over R times E raised to minus I theta. So here the magnitude inverted, the magnitude of W is equal to 1 over magnitude of Z, and angular reversed argue, which is W, which, minus of argue Z. So the condition for conformality here is dW dz. That means f of z should be minus of 1 over z square, which is different from 0. So z should be different from 0. Inversion is a conformal transformation given by W is equal to 1 over Z, which maps each point to its reciprocal inverse distance from the origin and the reverse angle, and preserves the magnitude of angle between the curves. Exponential mapping is also there. The exponential mapping is a conformal transformation that converts rectangular regions in the complex plane into circle and radical patterns while preserving angle. So for example, W is equal to e raised to z is the exponential mapping, which is e raised to x plus iy, which is e raised to x times cos y plus I sine y. So this is the exponential mapping. On that, the real part is u is equal to ex cos y, and the imaginary part is the power of x sine y. Therefore, the exponential mapping W is equal to e raised to z is the conformal transformation that maps vertical line in the z plane into circle and horizontal line in radial lines in W plane while preserving the angle. We already seen this bilinear or Mobius transformation, which is a very powerful conformal mapping that can map lines and circle into the complex plane to other lines or circles. And mathematically, we can express the bilinear transformations, which is W is equal to AZ plus B over CZ plus D. For AD minus BC is different from 0. So here, A, B, C, D are complex constants. Z is the complex variable in the Z plane, and W is the transformed variable in the W plane. And the condition for conformality is AD minus BC is different from 0, which ensures the transformation is non-degenerate. So this is just bilinear transformation, okay? So the bilinear transformations, conformal mapping of the form W is equal to AZ plus B over CZ plus D, with AD minus BC should be different from 0, and which maps line and circle in the Z plane to lines and circles in the W planes, preserving angle. And it is widely used in the complex analysis and aerodynamic flow transformation. So what are the key characteristics of the conformal transformation? So one of the key characters, angle preservation. And the second is scale invariance. And the third is Jacobian matrix. So most defining feature is that angle between intersecting curve remain the same after transformation, that is angle preservation. The distance are scaled, but the rotation of distance is preserved. And the scaling factor can vary from point to point, which is called scale invariance. Another is orientation. So some conformal mapping preserve orientation, like rotation, while others reverse it, like reflections. Okay, and the fourth one is the Jacobian matrix of conformal transformation is scale time and orthogonal matrix. So the Jacobian matrix should be defined. So let's see the Jacobian matrix. So the Jacobian matrix is fundamental concept in multivariate calculus and vector calculus. Okay, so in coordinate transformation, in fluid mechanics, and in aerodynamics. So it measures how the transformation stretches, rotates, or skew plays locally. So let's suppose the transformation, the form of variable x and y to u to and v. So u is equal to f of xy, v is equal to g of xy. These are the real and imaginary part of the transformed matrix. So the Jacobian matrix of the first order partial derivative is given as du dv, and the first column du dv, the du dx, the du dy is there, dv dx, and dv dy. So this actually are obtained from the what you call that the Riemann equation. Okay, from the Riemann equation, we can develop the Jacobian matrix. Okay, the determinant of the Jacobian matrix measure the local scaling factor of area under the transformation. So determinant of J is equals to du dx dv dy minus du dy dv dx, which should be, if it is the determinant is greater than 0, orientation preserved. If the determinant is less than 0, orientation reversed. And if the determinant is 0, it is just singularity point or locally collapsed area. Okay. Actually, in the case of finite element analysis, the excessive distortion of an object may cause the shape to distort excessively. That happens when the Jacobian matrix is equal to 0. So let's take example on that and see. Let u is equal to 2x plus 3y, b is equals to x minus y. Then the Jacobian matrix becomes what? du dx. So du dx is what? 2, only 2. And du dy, okay? Du dy gives us 3. dv dx gives us 1. And dv dy gives us minus 1. So 2, 3, 1, minus 1 is the Jacobian matrix. And we can find determinant. So the determinant of Jacobian matrix is 2 times minus 1 minus 3 times 1, which gives us minus 5. So the area is scaled by 5 and oriented reverse. Okay, so in the reverse orientation. The second example is given W is equal to U plus IV. F of Z is equals to Z plus Z is equals to X plus IY are given. So the Jacobian simply put in du dx dv dx du dy dv dy are there. So from the Cauchy-Riemann equation, we have du dx is equal to dv dy, and du dy is equal to minus of dv dx. So we can substitute this. So we can put it here. For example, in the second column, dv dx. Instead of dv dx, yeah, we can put du dx here. Okay, so it becomes what? The Jacobian du dx square plus du dy square, which is the magnitude of the derivative of f of z square. So which shows area is locally scaled by f prime of z squared and conforms angle preservation conformality. Okay. So once we understand this, let's go to the application of conformal transformation in Joukowski transformation. So using the Joukowski the above transformations, the fluid flow around geometry of an aerofoil can be analyzed as the flow around cylinder, the circular cylinder, whose symmetry simplifies the need of completion. So the name of this transformation is Joukowski. For actually the transformation, we have here the Z plane. Okay, the circular cylinder, the flow over rotating cylinder is in the XY plane. That means Z plane we call. And then the next aerofoil, which is transformed to the W plane. So this is W plane, and this is the Z plane. So use complex variables to map from one geometry to another. So the circular geometry changes to aerofoil shape here. So this is just a rotating cylinder, and this is an aerofoil. So that is called Joukowski's transformation. The Jokowiski's transformation is used because it has a property of transforming circles in the Z plane into shapes that resembles aerofoils in the W plane. So that is the Jokowisky transformation. And the function in Z plane is circle. So here it is a circular object. Okay, circle given by Z is equals to B times E raised to I theta, or which means Z is equal to B times sine theta plus I cos theta. Where B is the radius of the circle and range from 0 to 2 pi. Okay, and the Jokiski transformation is given by the function W of Z is equals to Z plus some lambda square over Z. Okay, so where W is the function in the transformed W plane and lambda is the transformation parameter that determines the resulting shape of the transformed function. Okay, so for lambda is equals to B, the circle is mapped into A at a plate going from minus 2B to 2B. For example, here, it is just a plate here. If lambda is equal to B, what we can get, this is XY plane or Z plane, and this is W plane. So on the W plane, we can see two objects. One is a plate simply, which goes from minus B to plus B. Okay. And setting the transformation parameter larger than B, when we set the transformation parameter larger than B, that lambda greater than B, then it changes the shape into elliptical shape, okay? Which causes the circle to be mapped into some elliptical shape. So this is a transformation. So from circle, we transformed plate and ellipse. When we change the transformation parameter lambda B, we can get simply a plate. And when we change the dimension lambda, which is greater than B, B is a circle diameter, no radius, then it immediately changes to ellipse. So the aerofoil shape is our main concern. So the aerofoil shape is realized by scaling or creating a circle in the Z plane with a center that is offset from the origin. If the circle in the Z plane is offset slightly, okay, by some factor S, the desired transformation parameter is given by lambda is equal to B minus S, where S is coordinates of the center of the circle. So, which gives the transformation in the W plane. So we have circle here, and the transformation parameter is lambda is equals to the circle radius minus some S. Immediately in the W plane, what we can get is the aerofoil shape. Okay, aerofoil shape. Point A is there, B, capital B's are there in the XY plane. And in our UV plane, we have both those 2 points are there. But the shifting of the circle diameter or radius, we can find an aerofoil shape. So the transformation in the W plane resembles the shape of an aerofoil symmetric about the x-axis. So here it is directly symmetric about the x-axis. The x-coordinate of the circle origin, therefore, determines the thickness distribution of the transformed aerofoil. We have also another type. If the center of the circle in the Z plane is also offset in the y-axis, if, look, it is offset in the y-axis, okay, center is changed to some point in the y-axis, what happened? According to the Jokowicz's transformation, it yields a symmetric aerofoil. This shows that the y coordinates of the circle center determines the curvature of the transformed aerofoil. So we can find this kind of aerofoil, which is curved or uh, uh, initially this one is symmetric aerofoil, but this is curved aerofoil. Okay, this is because of the y center offset. Uh, in addition to the circle in the Z plane being transformed to aerofoil in the W plane, the flow around the circle can also be transformed because of the previous mentioned angle preserving features of the conformal mapping. Therefore, this requires that the velocity potential and the stream function should be expressed as a complex function. And this can be represented for the velocity potential. W of z is equals to pi plus I psi. So pi is the velocity potential and psi is the stream function, as we know. So the flow pattern also change, not only the shape of aerofoil, but the flow pattern also change. The velocity potential as well as the stream function also changed. So when I come to the summary, from the aerodynamic point of view, uh, if we consider circle slightly offset from the origin along the negative real axis, that means to the negative y-axis, not real axis is x-axis actually, or 1 of 10 symmetric Joukowski aerofoil. Look, this happen, symmetric aerofoil happen only when it offset in the x-axis only, in the real axis, to the negative direction. That means this one, we can see. Yeah. For example, this is center. Okay, this is the center point for the circle, and it is shifted to the center, shifted to somewhere here in the x-axis. What happened? We can find this kind of minus 2b to 2b of the symmetric aerofoil. If the center shift in the imaginary axis, this is the shift in the center up. Center is here, and this thing is passing through this line, shifted to negative imaginary axis. What happened? We can find cambered aerofoil. The equation of the offset circle is z is equals to aei theta minus eb, where constant e is a small number. If the cylinder is displaced slightly along the complex axis as 1/10 cambered aerofoil. So when the offset in the y-axis or the imaginary axis, what we can get is cambered aerofoil. So these are some of important ideas. And also we can shift the velocity function also, the stream function and velocity function. So the complex representation of potential flow should be analyzed in the context of conformal mapping. So the basic flow used in potential flow theory are like uniform flow, source flow, sink flow, doublet flow, and vortex flow can also be represented using complex numbers. Okay. If a complex number, zeta, with both real and imaginary parts representing potential flow, then the form of number is zeta of z is equal to pi plus I psi. So pi is the velocity potential and the psi is the stream function. Okay, here both velocity potential and stream function are also themselves complex numbers. Okay, so for the uniform flow, we have zeta of z, which is equal to v infinity z, which is equal to pi plus I psi, which is v of v infinity times x plus iy. Okay, Z means x plus y, which is v infinity of x plus v infinity of y. Okay, that means with I times. Pi is equals to, then from that, what you can get, the real part of the velocity, pi is equal to v infinity x, which is v infinity r cos theta, which is similar to which we have discussed. And the imaginary part psi is equals to v infinity y, which is v infinity r sine theta. So that is for the uniform flow. We can refer our previous chapter. Again, for the source flow, we can define it in terms of source strengths. So zeta is equal to the source strength z by y 2 pi ln of z. So which is pi plus I psi, right? So which finally gives us the source strength over 2 pi ln r plus I times the source strength over 2 pi theta. So this is the real part and this is the imaginary part here. Again, vortex flow, we have similar approach. Again, duplex flow, similar approach. Okay, doublet flow. And the next is the Kuta conditions. So the leading edge of real aerofoil usually has a finite curvature and therefore presents no difficulty in analysis. Okay, that in the real three-dimensional wing. But for the bodies with sharp trailing edge, okay, for bodies with sharp trailing edge, like aerofoil, which are at a small angle of attack to free stream, the flow will adjust itself in such a way that the real stagnation point coincide with trailing edge. For the flat plate aerofoil, the real stagnation point is at z is equal to AE raised to I alpha. And according to the Kuta condition, it has been moved to the trailing edge. So zeta is equal to A times Z, which is equal to 2 times A through counterclockwise angular displacement of alpha. So that sine theta is, which is equals to minus of circulation over 2 pi u, and where is the circulation of the clockwise vortex. So this is just flow over cylinder. Okay. Okay, so now we are just summarizing the conformal mapping, which is called conformal transformation or angle preserving transformation, or sometimes we call it as biholomorphic map, which is a transformation that preserve local angle. An analytical function is conformal at any point where it has non-zero derivative. And consequently, any conformal mapping of complex variable which has continuous partial derivative is analytic. Conformal mapping is extremely important in complex analysis as well as in many areas of physics and engineering, like aerofoil analysis, as we have discussed. And it preserves the magnitude of angle, but not the orientation which is actually isogonal mapping also is there. In the case of isogonal mapping, it preserves the magnitude of angle, but not their orientation. So different transformations are here, and their formulas are presented here as their effect. Okay, transformation or translation, W is equal to Z plus A. So it moves a figure by an amount of A to A direction. Scaling, which can enlarge or reduce. Rotation, it rotates the figure. Rotating and scaling can rotate and scale the object. So W is equal to R times EI theta. So R is the scaling factor and EI theta is the rotation. Inversion is 1 over z, and exponential is e raised to z. So rectangular to polar grid. So this is just a simple summary what we have discussed. We have seen the conformal mapping, we have seen the Jacobian matrix. We have seen the definition of conformal transformation, which is a function that preserves angle and local shape, and commonly used in fluid mechanics, aerodynamics, and complex analysis. So we represent the conformal mapping W, the transformed plane W is equal to f of z, and z is the original plane, which is in the xy plane. So W is equal to U plus I, V is the complex transformed plane. And the types of conformal transformation which we have discussed: translation, scaling, rotation, scaling, inversion, exponential transformation, which we have discussed all. Again, each examples are given. For example, in the case of, for example, z is equal to 1 plus I, w is equals to 2I times I plus 1. Then we have transformed this plane into this type of plane. In the case of inverse, also, actually, we have this type of transformation. Yeah, these are actually transformations from in each case. Okay. So, and bilinear transformation also here. Again, the application of transformation, conformal transformation in the Joukowski transformation, in the Jacobian matrix iteration, all are presented in this slide. And I think this is sufficient for this course. Actually, we have some additional notes here, how we can transform. Everything is there. So if someone interested that he can see, some of them are already we discussed. Okay. Yeah. Yeah. Thank you very much. So this is all about conformal transformation.